All right. Welcome finally to our last unit of Unit 4. This is called Gibbs free energy. This is also another video meant mainly for honors, so if you're not in honors, feel free to watch, but this will not be on any quiz or test. However, if you're interested in AP Chemistry, highly recommend you watch this video. All right. So, a guy named, I believe, Josiah Gibbs, the guy who started Gibbs free energy, basically defined Gibbs free energy to represent the total amount of energy currently available for a reaction. So whether that's energy that it already had, whether it's energy it just gained based on the temperature, based on whatever, it's how much energy is currently available for a reaction. So if our change in free energy, designated by delta G, G standing for Gibbs, is positive, that means that for this reaction to occur, our system has to absorb energy somehow. That means our reaction is not spontaneous. Gibbs free energy is designed to be the main indicator of spontaneity. Enthalpy is a pretty good idea, whether endo and exothermic, but not enough. Entropy is also a good idea, but again, not enough. Gibbs is designed where, as you'll learn very soon, if delta G is positive, it's not spontaneous, and if it's negative, it will be spontaneous. For example, fire. Fire typically starts from wood. Okay, there is plenty of energy available for the wood. However, we can't really use it. We have to throw a lot of energy at it to get wood to burn. That means our delta G is very positive. That means that it's not spontaneous, which is very good. We are forced to randomly, just explode and light on fire. Kind of awkward. But nonetheless, delta G positive means non-spontaneous. If it's negative, that means our system will use up whatever energy it has and end up with less than it started, meaning it had enough to begin with, thus spontaneous. So again, like avalanches. But also you can think of it as it takes a lot of energy to put it back to where it began. Going back to that spilled milk example, it's really hard to get that milk back in the container. It's really hard to get the snow back up an avalanche. So, which makes sense that they're both pretty spontaneous. So an equation that relates pretty much all our thermodynamic constants together is this. Delta G equals delta G H minus T times delta S. Okay? So that means our free energy change is equal to our enthalpy change minus our entropy change times our temperature. So one thing I don't know if we ever quite remembered, delta G represents energy, which is going to be measured in joules. Delta H represents enthalpy, which is typically measured in joules. Temperature is typically measured in Kelvin. And entropy, I don't know if I ever told you this, is actually measured in joules per Kelvin. It represents how much energy is dispersed based on a certain temperature. So when you multiply that out, K's will cancel out, you'll end up with just joules, which makes sense when we're talking about how much energy is available. So, let's try this. A reaction that has a delta H of negative 76 kilojoules and a delta S of negative 117 joules per Kelvin. Is that spontaneous at basically room temperature? Well, delta G is what we're solving for since we're looking for spontaneity, equals delta H minus T delta S. A way that kind of helps me remember this is delta G equals hits. H, think of that as kind of an I, T, S. I know it's not great, but it kind of helps you remember something. Good luck. It works for me. So first off, do notice that is negative 76 kilojoules, which means that is negative 76,000 joules. So we have negative 76,000 joules. I kept them in joules because my entropy was in joules, which kind of makes my life easier. But minus 298.15 times negative 117. Multiply that together, and you get negative 41,100 joules. Now, this is in sig figs. Keep in mind that this result of this number would get down to 3 sig figs, but it's not going to have a decimal after it. So that means we basically can just write the whole number after we put that in the 3 sig figs. Anyways, that is definitely extremely, okay, not extremely actually, but that is a negative delta G. That means this reaction is spontaneous. Again, because our delta G is negative. There you go. That's Gibbs. Sometimes you do a bit more, but really this is the most popular thing people do with Gibbs. All right, so suppose that a reaction has delta H and delta S. At what temperature will it change from spontaneous to non-spontaneous? So this is like a hard version, kind of. So we basically know that our temperature, spontaneity happens will change when Gibbs is 0. So below that, it's spontaneous. Above 0, it's not spontaneous. Technically, 0 or above is not spontaneous. So all we got to do is set our Gibbs to 0. That says that, again, delta G equals hits. So 0 is equal to, again, we have kilojoules this time, so negative 28,000 minus T, or we're not sure what that is, but we're going to multiply that by negative 60. So that gets us 28,000 is equal to 60 T. That means our temperature will be at 470 Kelvin. So there you go. Now this is actually wordly because typically you're thinking you're going to raise my temperature, but that means that actually below that temperature it will not be spontaneous, and above that temperature it will be spontaneous because you have enough energy. So with that, thanks for watching. Here's some practice. All right, tons of words on the screen, I know, but as always, thank you for watching. Enjoy your practice.